Welcome guys to another session of MSI Hub. Now in this session we are going to deal with Euclidean geometry, which is geometry of what? Circles. Now in Euclidean geometry, just like any other maths topic, you need tools, but I think tools are more important when you deal with specifically geometry. What are those tools? Before I start with those tools, like whenever you do anything, whenever you, let's say you want to fix a car, what do you do? What do you need if you want to fix a car? You need tools. If you want to cook in the kitchen, you can't just cook. Let's say you're cooking porridge, you just can't cook porridge without having proper tools like spoons and a pot and whatnot. So just in Euclidean geometry as well, you need tools in order to solve Euclidean geometry. So I'm gonna quickly discuss those tools before we get into the gist of Euclidean geometry. Looking at those tools are part of your revision. What are those tools? Like I said, they are part of your revision. Those tools are the relationship between straight lines, and the first one that we have there is alternate angles. And you know that we see, or we define, or we identify alternating angles by what? By a Z pattern. Now you can't just have a Z pattern in any other case. For you to have alternating angles, your lines must be what? Must be parallel, just like these two lines over here. These two lines are parallel, and we have those two orange dots as our alternating angles, as well as corresponding angles. If you have two parallel lines, you would have alternating angles. If these are my parallel lines, these two alternating angles will be equal. And we have co-interior angles, angles that are within, or angles that are inside the parallel lines. If these are my parallel lines, the angles marked with a circle and a star would be supplementary, and they would equal to 180 degrees. Also, if you have two straight lines that intersect, they form what we call alternating angles. Now if you have these two lines that intersect, it means my alternating angles, this angle and this angle over here, would be equal, and this angle and this angle over here would also be equal. Now moving on, also part of your tools that you're gonna need, you will also need to learn, or you'll also need to remind yourself of triangles. And I've included only two triangles in this slide, which I think will help you solve problems pertaining to Euclidean geometry. The most important one is this one over here, the isosceles triangle. If these two lines are equal, it would mean you would have equal angles. Right angle triangle would also be important. Equilateral would also be important. But the one that I need you guys to focus on is this one over here, which comes up almost 90% of the time. You would need to learn this in order to solve whatever problems that you'll be dealing with in Euclidean geometry. Now moving on to my next slide, subtends defined. Now this term is used a lot, and for you to be able to understand what it means to subtend, we need to actually try to define it and try to explain it in a much simpler way. So I've written the easiest definition for what it means if you say something is subtended, I would say to take up or extend the side opposite an angle or an arc. Now let's say you are looking at a wall. If this is my wall and this is your eye looking at this wall, let me just extend it a little bit. Yeah, if this is my wall and you are looking at it and your ray would come over here, and then another ray of your eye would come over here. Now your view from that angle, your view of the wall from top to bottom, these would say this is the angle that subtends this wall. So we would say this angle subtends this wall, but then in a case of Euclidean geometry, it would mean this angle is subtended by a chord, or in some cases it would be subtended by an arc. So to subtend, I would say basically means to support, because it holds these rays, they hold the wall on both sides. So I would say to subtend, it basically means to hold or to support. Now moving on to our theorems of Euclidean geometry. We are going to identify or define a few concepts when we deal with Euclidean geometry, and try to understand what a chord is, what a diameter is, and what a tangent is. So I'm going to start by drawing my circle. And have a line that joins from one end of my circle to the next end of my circle. Now this line that joins 2 points on the circumference, we call it A. This line that joins 2 points on my circumference, we call it a chord. And then if this is my center, doesn't look much of a center, but let's take it as my center, and then I have a line that passes through my center, this line would be my diameter. And let's say I have a line that joins the center of a circle to a point in a circle. From this center to a point in a circle. From my center to a point in a circle. This line would be my radius. This line would be my radius. This would be my diameter. If I have a line that touches my circle at one point, we would call this line a tangent. Let's say it touches exactly at this point over here. Let's say it touches exactly at this point over here. If they touch at that point over there, this would be my what? My tangent. Now we are going to move. We just discussed straight lines in a circle. Now we are going to discuss subtended angles. I'm going to start by drawing my circle. Now let's say we have center O. Let's say we have center O. If this is center O, and then we have, I'm gonna call this chord AB, or arc AB, and then we have two lines that are drawn there. Now we would say arc AB, or chord AB. Oopsie. Let me just draw this. I would say chord AB or arc AB subtends O at the center. Let me just say this is O1. This is O1. Now arc AB would subtend O1 at the center, and if I extend my lines to the circumference and call this C, we would say again arc AB subtend C at the circumference. At circumference, right? Moving on to theorem number 2, which basically says an angle at the center is twice the angle at the circumference. Now I'm gonna try to illustrate it by drawing it for you, what we mean by that. If I have, I would say this is chord BC, and then I would have my center over there, and then I would have maybe another angle over there, and then I would say this is O, and then this would be A. Now what this theorem says, it says if, let's say, I would call this angle X, and both of these angles are subtended by this chord or this arc, it basically says this angle is twice the angle at what? At the center. It's twice the angle at the center. Yeah? Meaning you would write this as O, angle O is twice angle A. Alright, let's look at another theorem. I'm gonna draw my circle, and then let's say this is again my center, and then I would have a line that passes through the center to the other end of the circumference. What did we say this line is? This line is a what? It's a circumference. And then let's say I have this line is a diameter. Sorry, it's a diameter. Let's say I have two chords that go on like this. Now, if I have a line that passes through the center, now this angle that is subtended by my diameter is equals to 90 degrees. So this angle over here would equal to 90 degrees simply because it is subtended by what? A diameter. This is theorem number 3. Moving on to theorem number 4. Now, theorem number 4 basically talks about angles in the same segment. Let's say, for instance, I have an arc. If this is my arc, and then I subtend an angle over there, and then I subtend another angle over there, and then let me have my center. Let me have my center. I will call this arc AC. This would be my arc AC. Can you see these two angles are subtended by the same arc? I will try to highlight it for you. From over there to there, over there to there. Now, what is common with these two angles is that they are subtended by the same arc. They are subtended by the same arc. Now, if two angles are subtended by the same arc, which is arc AC, it means these two angles are equal. Meaning, if this angle is x, this angle will also be x. Now we are going to move to another important theorem when dealing with Euclidean geometry. Now, this theorem basically talks about the relationship between a quadrilateral that is within, or the vertices of those quadrilateral touch the circumference of what? Of a circle. Now let's look at this theorem. It says a cyclic quadrilateral has all its vertices on the circumference of the circle. Now guys, that is a very important part. All its vertices are in the circumferences of the circle. That makes that a what? A cyclic quadrilateral with all its vertices at the circumference of the circle. Let's say we had a quadrilateral that has one vertex or one point of that quadrilateral not touching the circumference. And let's say this is, let's call this E. Let's call this E. Now, the first one touches at this point, at this point, and at this point, and at this point. All the vertices touch, all the points touch our circumference. But now let's construct another one, which is D E B C. Now one point of this quadrilateral doesn't touch the circumference. Does it make it a cyclic quadrilateral? No, it doesn't, simply because it doesn't touch the circumference, which is one of the mistakes that you guys normally do. If you see a quadrilateral that is inside the circle, you don't check whether all the points actually touch the circumference. So you must make sure that all the 4 points touch the circumference, which will make it a cyclic quadrilateral. Now, what do they say about the cyclic quadrilateral? They say opposite angles add up to 180 degrees. Meaning, angle A and angle C put together would give you 180. Angle D and angle B put together will give you 180. Now, another important one, if I was to extend C to E and form an exterior angle, this exterior angle would equal the opposite angle, which is angle A, meaning A would equal to E. Now, let's have a look at our last theorem, which is Tan-Cot theorem, which is very important when we deal with Euclidean geometry. Now, it says the angle formed between a tangent to a circle and a chord drawn from the point of contact is equal to the angle subtended by the same chord in the other segment of our triangle. For instance, of our circle. For instance, if we have this as my tangent, and then I would have this as angle X, and then this is my chord, and then this angle between a tan and a chord, and the angle that is subtended by the same chord, these two angles would be equal. Similarly, this angle between a tangent and my chord would equal to this angle which is subtended by the same chord. That's basically it. Now let's have a look at one of the questions that was set for the matrix. It's 2017 paper. We are going to look at paper 2, question 8, and try to tackle that paper and try to put everything together into perspective and try to explain it to you guys. So let's have a look at that paper. All right, let's look at this Department of Basic Education February to March question paper. It was taken from 2017. So I started, as we've been discussing, Euclidean geometry. So that part of Euclidean geometry is question number 8. Now question number 8 says, in the diagram PQRS, it's a cyclic quadrilateral, so that's given. You don't need to prove it. ST is a tangent. So I'm going to just highlight what is very important. We know that ST is a tangent to the circle at S. So this is where it touches it at S. This is where it touches it. And chord SR is produced at V. So chord SR is produced where? At V. Now this is very important. This is very important because each and every word actually means something. It actually means a tool that you will need to solve this problem. Simply by saying SR is produced at V, it means you must have something in mind. So as we solve this, we will find out what we actually need to have in mind. And then they say PQ is equals to QR. Now what does that tell us? What does that tell us? What that tells us, it means these two angles would be equal. And then they say S2 would be 108 degrees. So let's read what the first question says. The first question says, determine with reasons the size of the following angles. The first one that we need to find is angle Q. Now, if this is angle Q, and then we are given this as a what? As a cyclic quad, can we look at the opposite angle and see if we can solve it that way? Yes, let's try it and have a look. So Q is opposite angle S2, and then angle S2 we are given it as 108 degrees. Now that we know that this is a cyclic quad, we would know that this angle put together will give you 180. So it means angle Q plus angle S2 would give us 180 degrees. My reason being opposite angles of a cyclic quad. Opposite angles of a cyclic quad, meaning now my angle Q would equal 180 minus 108, which will give us 72 degrees. So angle Q would be 72 degrees. Moving on to 1.2. 1.2, they need to find the size of R2, and this is my R2. This angle here is my R2. Now, remember I said, given these two sides as equal, it means now we are dealing with an isosceles triangle, which means this side, this angle would equal this angle, meaning P1 would equal R2. My reason is going to be isosceles triangle. And I can say angles opposite equal sides, equal sides. Equal sides. All right, now that I have established that this angle equals this angle, and I know the value of Q, which is 72, and let me just enclose this. Let me just enclose this and have triangle PQR, and have triangle PQR. This is 8.2. This is 8.2. Now we know that the sum of angles of a triangle will give you 180. So it means that P angle P1 plus angle Q plus angle R2 plus angle R2 would equal 180 degrees. My reason is going to be sum of angles of a triangle. Sum of angles in a triangle. Now remember, we have deduced that angle P equals angle R2 simply because they are angles opposite equal sides. So remember, we said these two angles are equal simply because they are angles between these two sides that are equal. It simply means now these opposite angles would also be equal, meaning we would say P1 equals R2. Now if they are equal, I can simply make this P1 R2 as well, meaning from this statement that we just had, I can say R2 plus angle Q plus another RQ, another R2 equals 180. And then if I put these two together, I'll have 2R2 equals 180 equals 180 minus 72, and then I can simply divide by 2 in order to have R on one side, divide by 2, and then my R2 would equal 180 minus 72 divided by 2, which would give me 54. Which would give me 54. All right, let's have a look at (8.3). Now 8.3, we need to find the size of P2. Let's go and have a look where P2 is. If this is P2. So they need us to find the size of that P2. Now remember, in our question they said ST is a tangent. ST is a what? ST is our tangent. Meaning we can have a look at this angle and this angle too, and simply say P2 equals S1. S1, we have the value of S1, we have the size of S1, which is 42. So the size of P2 will also be 42. And what's going to be my reason? My reason will be tan cot theorem. My reason will be tan cot theorem. My reason will be tan cot theorem. All right, let's look at the next one. Which is R3. Let's see where R3 is. This is R3. This is R3. Now remember what I said about this statement here. When they say cot SR is produced at V. Cot SR is produced at V. Now, why is that statement important? Because simply by telling us SR is produced at B, it means now these angles which lie on this line, they can simply be angles on a straight line. If this chord is produced at V, it means this line is a straight line. We can assume that this line is a straight line. So now that we have that information, we can try and solve our problem. We can try and solve our problem. Now before we solve our problem, we know the size of R2. We know the size of R3. But then we don't know the size of R1. We don't know the size of R1. So before we can solve R3, we need to get R1 first. So how are we going to get R1? We know this angle P2, we know this angle S2, and we know that we have now. Let's shift our focus to this triangle PRS. Let's shift our focus there and say this is 8.4 and say P2 plus S2 plus R1 would equal 180 degrees, which would be, my reason would be sum of angles in triangle. Meaning, remember we had the value of P2 as 42 S2 was 108. S2 was 108 plus R1 equals 180. Now R1 would equal, if we take everything on the other side, 180 minus 42 minus 108 would give me 30. So the size of R1 would be 30 degrees. Now that we have the size of R1, we can now solve this angle R3. We can solve this angle R3 by saying, therefore, R3 plus R2 plus R1 would equal 180 degrees. My reason would be angles on a straight line, angles on a straight line, angles on a straight line. Since we know the values of the other two angles, my R3 will equal 180 minus 30 minus 54, which will give me 96 degrees. There you go. Now, the reason I chose this question is because it simply includes most of the theorems. It includes cyclic quadrilateral. It includes straight line relationships. It includes tangents, and I think it was a nice problem to solve. Thank you very much, guys, for your viewing. See you next time. I hope you enjoyed this lesson. Thank you very much.